Okay, what we're going to do is we're going to do a little modeling. We're going to take the data that we have here, this time and distance data, and we are going to uh, derive an equation for it through graphical analysis. So what we'll do first is we're going to go ahead and graph this data and decide which of the 5 graphs that it fits. Is it a top opening parabola, side opening parabola, constant graph, linear graph, or an inverse graph? So let's go ahead and graph this. We'll start with 0, 0 down here. This is going to be time on the x-axis because that's our dependent variable um, listed first. And we've got our distance, which is going to be on our y-axis. So let's go ahead and set up our scales. As far as the x-axis goes, we should be able to go up by ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, that puts me right there. So I'll go 2, 4, 6, 8, and 10 is at the T. You know what? Let me just move that over a bit so I can fit that in there. 10, and again, we'll put our time over here. That's on our x-axis. As far as the y-axis goes, let's see, we've got to get up to 300. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Going up by 30 should work, so it'd be 30, 60, 90, 120, 150, 180, 210, 240, 270, 300. Time is in seconds, and distance is in meters. Alright, so we're ready to go ahead and start graphing. 0, 0 is one of our points, so we'll plot that. 0, 0. And then 1 second, we are at a distance of 3 meters. That's 30. We're going to be really close to the bottom here. So we'll just put a dot there. At 2 seconds, we're going to be at almost 50. So if that's 30, 40, 50, it's got to be up about there. At 4 seconds, oops, sorry about that, plotted wrong. Actually, at 2 seconds, we're going to be at about 12, so 2, roughly about halfway up there. Since this is 30 and 15 is about halfway, 12 is going to be a little less than that. 4 will be at almost 50, so that'd be about here. 6 is going to be at 108, so that's 90, like 100, 110, it's going to be about there. 8 is almost at 200, so it's 8, so it's 180, 190, it's about 200 right there. And then 10 is at 300. 10 and 300. So we've got distance versus time is our distance versus time is our title. And certainly if I were able to take a straight edge and drop a straight line through this, let's try to drop a straight line through this. If I try to draw a straight line through this, clearly a straight line does not fit. This looks a lot like a top opening parabola. You can see the nice sweeping curve going up, top opening parabola. In order to straighten out a top opening parabola, what we're going to do is we're going to square the x values. So what I'm going to do is create another column here. And this becomes time squared in the units of meters squared. Write that out a little better. Time squared in the units of meters squared. So what we're going to do is we're going to square everything in the x column. So 0 squared is going to be 0, 1 squared is 1, 2 squared is 4, 4 squared is 16, 6 squared is 36, 8 squared is 64, and 10 squared is 100. All right, I am now going to make a second graph, and this second graph should wind up being linear, because what I'm going to do is I'm going to ignore this data here. I'm going to make a new graph. Go ahead and make a new graph here. I'm still going up to 300, so I'm going to do that. And I'm going to be going up to 100. So I got to go to 100 here on the X. So that'd be 10, 20, 30, 40, 50, 60, 70, 80, 90. Rats, you know what would be nice is if I could move this over, and I think I can. So I will do that. So this is time in seconds. And then what I can do is go ahead and graph this. This will be, let's see here, 0, 10, 30. You know what, let me do this. That'll be 10, 20, 30, 40, 50, 60, 70, 70, 80. What? Oh, I didn't move my graph over rats. Alright, let's try this again. So I want here. It's going to be kind of tight, but I can do this. Right about here, go down here. So this will be 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. And then going up, it's the same as before. 0, 30, 60, 120, 180, 240, and then up at the top here is 300. All right, so I'm ready to go ahead and plot some points. So here's what I'll do. I've got 0, 0 again. Again, now this becomes my x here. So it's going to be 0, 0. Plot that point. And then 1 and 3. So that's going to be really close to the bottom here. It's going to be practically on top of that. 4 and 12. So it's 10. And it's going to be, you know, down here somewhere. Uh, 16 and like 50. So 16 and like 50 will be up here. And 36, which is almost 40, and like 108. So it's 90, that's 108, so it's about here. And let's see here, 64 and 192, so 64 and almost 200. So it's about here-ish. And then 100 and 300. So that'd be up here. A fairly straight line. So what I'm going to do is put a straight line through this. A fairly straight line. Now at this point, I put a best fit line through there. I got 1 point below, 1 point above. I hit, you know, the rest of the points. It's linearized. Let's see here, this is distance again in meters. And this over here is going to be time again. but it's not going to be time this time. It's going to be time squared in seconds squared. I just noticed I mislabeled this. Let me fix this. This should be time in seconds squared. So at this point, what I can do is I can figure out the slope of the line and write an equation for this straight line like we've done before. So I'm going to pick 2 points on this line that work out nicely, stuff that hits at some nice intersections. So I'm going to choose, let's see here, anything hits some nice intersections. This guy's close. I'm going to take this guy right here, and I'll take about here maybe. So we're looking at 120 and about 45. So I'm looking at this here, and this here, and this here, and this here. So I got my change in x, I got my change in y. So that slope is going to be equal to change in y over change in x. So my change in y is going to be equal to final minus initial, which is going to be about 240, 270, right? Because these guys go up by 30, so it's 270 divided by, or excuse me, minus 120 divided by my x. This is my final here, which is 90 minus, let's see, that would be 40, so that'd be 50, so it's about 45. So that's going to be equal to 270 minus 120. I got a calculator here. I do not. Let's do this. So I got 270. Huh, that's not working. That stinks. 270. Yeah, that's not working. Rats. All right, let's see here. 270. That's 150. I guess I'll do it in my head. And that's 45. 90 minus that. So let's see here. 150 divided by, that's almost 3. 150 divided by 45 is going to be equal to 3.33, 3 and a third. And this is, y is in meters. And then the x is in seconds squared, so that's meters per second squared. Goes through 0, 0. So my final equation is distance, which is my y-axis, distance, is equal to slope, 3.3 meters per second squared, times time squared. That is the equation that fits this data.